गुरुर्ब्रह्मा गुरुर्विष्णु गुरुर्देवो महेश्वरा गुरुसाक्षात् परब्रह्म तस्मै श्री गुरवे नमः.
Good morning, students. In today's session, we'll discuss about conversion of one number system from another number system. So today's topic is number system conversion. We can convert decimal number into binary number into decimal number. So first let me take decimal number system to binary number system conversion. The decimal number system 25. How it is converted into a binary number system. So the 25 is continuously divided by base of the binary number system, and the remainder is noted in the respective stages of the calculation process. So in this example, the decimal 25 should be converted into binary number system. This 25 should be continuously divided by the base of the target number system. In this example, that is 2. Okay, the remainder will be noted at the right side every time after dividing the number. So let me divide that and show you how exactly conversion can take place. The value 25 is divided by 2. So 25 cannot be completely divided by 2. The nearest value is 2 times 12, 24. So 25 minus 24 gives the remainder 1. I am writing the remainder at the right side. This is the remainder. Okay. So remainder is 1 of the operation division. Now we have the quotient part should be arrive at 0. Until to that level, it should this value should be divided by 2. So 12 is divided by 2. So we can completely divide 12. So 2 times 6 gives 12 exactly. The difference between 12 minus 12 is 0. I am writing 0 at the right side. Then 6 cannot again should be divided by 2. So 2 times 3 gives 6. Difference between 6 and the 6 of the division gives no remainder at all. 2 ones are 2. That is the nearest value. 2 to the 4. Okay, so that cannot be possible. So 3 can be divided by 1 time. That gives the remainder 1. And 1, the quotient is lesser than the value 2. At this level we have to stop. The 1 remains the remainder in this case. So 1 is written as it is. Now we have to write from bottom to top. When we write from bottom to top, so the value of this operation gives 1, 1, 0, 0, 1. It should be written like this. So 1, 1, 0, 0, 1 in this, 1 is the MSB and the rightmost digit is the LSB. You know, most significant bit and LSB, least significant bit. Here, which one is the MSB part? The bottom one is the MSB part and the top one is the LSB part. So it is better always you write like this an arrow or know the position of the LSB and the MSB in the sequence of this operation. I hope you have understood. So this is how a decimal number can be converted to binary number. Let me take another example. The another example, please try to solve if you understand this operation. Say the number is, this time say 35.625. 35.625 is the decimal number. What is its binary equivalent? Let us convert. But here in this example, there are two parts of the number. This is the real number. There is an integral part, there is a fraction part. Integral part follows one rule, fraction part follows another rule. Let us do it separately. So, the integral part 35 is taken and let us again divide it by 2 continuously until the quotient remains 0 or lesser than the base of the binary number system. So, this one, 2 ones are 2, 2 sevens are. So, 2 times 17, 34. The remainder is 1, I am writing at the right side. So, 2 times 8 gives 16, difference is 1. 2 times 4 or 4 times 2 is 8, remainder is 0. 2 times 2 is 4, remainder is 0. Then 2 times 1 is 2, remainder is 0. And 1 cannot be divided and that 1 is written as it is. 1 is written as it is. Now you can see it is. How do we write this 110011? Because we can also write 110001. From the previous example, one should know, okay, this arrow writing from bottom to top indicates this digit will come at the MSB place and this digit will come at the LSB place. So we write from left to right, starting from the bottom digit at the remainder places. Okay. So how can this be written? 100, 0, 1 and 1 dot. Put the dot as it is. Now take the fractional part. How is the fractional part is converted? Is it going to be divided? No. Answer is no. The fractional part of the decimal number is multiplied by the target number system. In this example, it is 2. So, 0.625 is multiplied by 2. When we multiply by 2, what is the answer we get from this result? That I am writing at this right side. Okay. So, it is 0 and carry 1 and 5 and 2.1. So, that is 1.250 is the answer of 0.625 into 2 will give 1.250. Now you have to consider only the fractional part of the result of the multiplication. Okay, if I write the fractional part in the next step, the value remains 0.250. Then what is the integral part digit? That should be written separately. So here I am writing at the left side. You can write at any part, any side, either the left side of this calculation or the right side of this calculation. This is a carry. Okay, what we get from this multiplication. Okay, I hope you understood. Now, 0.250 is multiplied by 2 again. This will give the result 0.500000. Any zero you can add, no problem. But in the integral part, nothing is appearing, so that can be treated as 0, no? Okay. Now the 0 is the carry Now what is the fractional part number we are getting? 0.500. Use that 0.500 again, multiply it by 2. That gives the result 0.500 into 2, 1.000. Now in the integral part, 1 is there, this one I am writing at the left side. At the left side. And the fractional part I am carrying to the next stage. But you can see at the fractional part only 0 is remaining. When we get the 0 at the fractional part, then we have to stop this calculation process of multiplication. Here we have to stop. This is the end of the calculation. So you see the carry here, 101 is coming. So this should be written from top to bottom. From top to bottom. What is the top value? 1. So the top value 1, the next value and the bottom value is 1. So here in the fractional part, this one is the MSB and this one is LSB. In the integral part, the leftmost digit in the integral part is MSB, the rightmost digit is the LSB. Okay. So what you can see here is I started writing from top to bottom. That is, this place can be called MSB and this digit can be considered as LSB. So we have to write from top to bottom in the case of fractions, and bottom to top if it is the result of the integral part calculation. This is how we calculate or we convert from decimal number to binary number. Next, we move on to how a binary number is converted into a decimal number. So we have the binary number here. Okay, we have the binary number. Okay, what is the binary number we have? Let me take the same example here. Or any number for that matter you can take. So now binary number to decimal number system. So from binary number to decimal, let me take an example. 10101 is the binary number. How do we indicate that it is a binary number? Subscription 2 is written. So what is the decimal equivalent of this? Now the target, okay, so is decimal number. Therefore what we should do is, we have to get the weightage of every position of this digit. That is, see, 10101. What is its position in the position number system? This is 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3 and 2 to the power of 4. Okay. What is 2 to the power of 0? 2 to the power of 0 is 1, 2 to the power of 1 is 2, 2 to the power of 2 is 4, 2 to the power of 3 is 8, 2 to the power of 4 is 16. Okay, so we got this. Now, the positional value is going to be multiplied by the place value of the binary digit. So, this number 16 into 1 plus 8 into 0 plus 4 into 1 plus 2 into 0 plus 1 into 1. Okay, so the number 16, 0, 4, 0 and 1. 16 plus 4, 20 plus 1, 21 is the decimal equivalent of 10101. Is this answer correct? Let us verify whether this answer is correct or not. You know from the previous discussion or the topic how a decimal number can be converted to binary number. So 21 is the decimal number. I am converting it into binary number. So 2 times 12 is 20, difference is 1, 2 5s are 10, difference is 0, 2 2s are 4, difference is 1, 2 1s are 2, difference is 0, and 1 cannot be divided by 2. This is written as it is. Now from bottom to top, if you draw, this is how we can write. So this number 10101, and this binary number 10101 is matching, therefore the calculation is correct. Octal number system, decimal number to octal number system. Let me take a simple number. Okay, so the decimal number, say 35. What is its octal equivalent? Now the rule is again same. Divide the 35 by the target number system, that is octal number system. What is the base of octal number system? It is 8. So 35 is divided by 8. 8 times 4 is 32. Difference between 35 and 32 is 3. Then 4 cannot be divided by 8. So the remainder is 4 as it is, should be carried. Okay. Now here also we have to start writing from bottom to top. It is not 33 4, but it is 4 and 3. 4 and 3. So this is the octal equivalent of the decimal 35. Is this? Now let us take another example. Say another example is say 61. 61. What is its octal equivalent? 61 is divided by 8. 8 times 7, 56. The remainder is 5. And here also the 7 cannot be divided by 8. So the remainder is 7. The result is 7, 5. It is not 75. It is 75. Okay. Now, let me take these two examples for conversion from octal number system to decimal number system. So that is, what is, suppose the 43 is given, what is its decimal equivalent? What is its decimal equivalent? 43, 4, 3 and 7, 5. So, let us use the positional value of the 4, 3 in octal number system. So that is 4, 3, the 3 is in the unit place 8 to the power of 0 and 4 is in the 8 to the power of 1 place. What is 8 to the power of 0? Is 1. 8 to the power of 1 is 8. So this value is multiplied by the face value of the octal number 43. So that is 8 into 4 plus 1 into 3. Okay. So this value and this value is multiplied. So the positional value multiplied with the face value of the digit. This is the positional value and this is the face value. So 8 times 4, 8 times 4 is 32 plus 1 times 3 is 3. The final answer is 35. So it is the decimal number for this 43. Then another example, 75 is there in the octal number. 75, take its position in terms of binary, in terms of octal number system, 8 to the power of 0 and this is in 8 to the power of 1. What is the place value of this? 8 to the power of 1 is 8, 8 to the power of 0 is 1. Okay. So, what is 7 times 8? What is 5 times 1? So, that comes to 61. 61 is the decimal equivalent of 75. Next is decimal number to hexadecimal number system conversion. So the decimal number here I am taking say 56. How it is converted to hexadecimal? Okay. So again the procedure is same. Base of the hexadecimal number is 16. Divide 56 by 16. Okay. So what is the nearest value of this? You can calculate. Okay. So those work from commerce background. So calculation can be done like this. You please make a working of multiplication. 48, 16 fours are 64. Now 48 and 64 is there. Which result we can take? Such 64 is exceeding the number 56. Therefore, equivalent or lesser than the 56 should be taken. In this example, 16 times 3, 48 is the nearest value. Now, we can take 48. What is the difference between 56 and 48? 56 and 48 difference, you can see it is 8. Difference is 8. This difference is the, okay, is the remainder. So, the 16 times 3 is 48. This 3 should be written in the next step. Okay, this 3 should be divided by 16. Can we divide 3 by 16? No, we cannot divide 3 by 16. Therefore, 3 should be written as it is. So, this number is 3 and 8. 38, what is its decimal equivalent? Now we have to take the positional value and multiply with the face value of 38. So it goes like this. So 3 and 8. What is the position of 8 in this? Is 16 to the power of 0. 3 in this is 16 to the power of 1. So what is 16 to the power of 1? 16 to the power of 1 is 16 and 16 to the power of 0 is 1. So let us multiply this. So 6 3s are 18, 1 is carry. Okay, 3 1s are 3 and 4 and this becomes 8. You add these two. If we add these to 48 plus 8, then the final answer we get is 56. This 56 is the binary decimal equivalent for the hexadecimal 38. This is how the conversion from decimal to hexadecimal and hexadecimal to decimal takes. Now let us see how the binary number is converted into octal number system. So here I am showing you a very simple and shortcut method. Carefully observe. An example can be taken. The example is say 1010011 is the binary number. How this number is converted into octal number system? A very shortcut method. Okay. A very shortcut method is, now look at the binary number. I am writing the same at the bottom. Which one is the least significant bit here? The rightmost, most significant bit at the left side. Start from the LSB. Make a group of 3 binary digits. A group of 3 binary digits from the LSB, please. So I am just marking it for understanding purpose. 3 digits from the LSB place, 1, 1 and 0, and from here another 3 digits, 0, 1, 0, and remaining only 1 bit is there, so you have to add or prefix the zeros to the extent of length 3 binary digits. That makes it 001. Okay, like this you just write, okay, by making the group of 3 binary digits and find its decimal equivalent. What is the decimal equivalent of this? Is 1. What is the decimal equivalent of this? Is 2. What is the decimal equivalent of this? Is 3. Is our answer correct? You can easily compute and get to know. Okay, now this 1, 2, 3 is the octal equivalent of the binary 1010011. Okay, now how is the octal number is converted to binary number system? How is the octal number system is converted to binary number? Let me take a octal number here. Again, the octal number I am taking here is 123 is the octal number. Now, what is the binary equivalent of this octal number? Now, this should not be read as 123 from the beginning I am telling. So it should be taken as an individual digit. Take the individual digit of the octal number, that is 1, 2 and 3. Find its binary by dividing. So 1 is divided by 2. 1 cannot be divided by 2. The remainder is 1. So the result of this one in terms of binary is 1. Okay. So whatever the result we get, it should be a group of 3 binary digits. So the 3, to make it 3 binary digits, it should not be written, okay, to the right side, but it should be written to the left side. So the 1 should be prefixed with the 2 binary zeros to make it as a pair, a group of 3 binary digits. So this is the binary equivalent of octal 1. The next is 2. Okay. The 2 is divided by the binary base number 2. 2 times 1 gives the difference 0. 1 cannot be divided, so the remainder is 1. So how this is written? It is written from top to bottom. So 1 0 is the result of the process or the calculation. Now there are 2 digits here. We have to make the pair of 3 digits, a group of 3 digits. Okay, so 0 is prefixed to this result to make a group of 3 digits. So that goes the final answer for the octal 2. Then we take the octal number 3 separately, convert this by dividing by 2. So 2 ones are 2, remainder is 1. 1 cannot be divided, so therefore it should be written as 1. So from the calculation, so we obtained 1 and 1, only 2 digits we got for 3. But we have to make the group of 3 binary digits to convert this binary to octal. So therefore I am prefixing 0 to this number. This stage is very, very important. If you miss this stage, then the result will be wrong. Okay. Now what is the final answer? The final answer is, so 0 0 1, 0 1 0 and 0 1 1. Is the result of octal 1 2 3 conversion to binary number system. Dear students, let us see how the binary number system, binary value is converted to hexadecimal number. Okay, so let me take a example binary number here. This is the binary number. Now, what is the equivalent hexadecimal number? Again, here I am discussing the shortcut method, how this number can be easily converted into hexadecimal. For conversion of binary to hexa, in the shortcut method, we group 4 binary digits and we obtain the decimal value of that group of 4 binary digits is the result of an hexadecimal. It is very simple. Okay. So again we have to start from the least significant bit and extend it to most significant bit, then make a group of 4 binary digits. So I am rewriting the same value, that is 1 0 1 1 0 0 1 1 0. Okay. So most significant, least significant digit is 0. From here make a group of 4 binary digits. Then remaining also make a group of 4 binary digit. Then only 1 digit is remaining. So let me add or prefix 0 to make it a length of 4 binary digits. Let us do this working first. Once the grouping is done, then find its decimal equivalent. So the decimal equivalent of this group is 1. Decimal equivalent of this group, that is, so here 1, 2, 4 is there. So that comes to 6, and this is also 6. Now this 1 6 6 is the hexadecimal number for the binary number. Again, from hexadecimal to binary we can easily calculate, that is, you take the each digit of the hexadecimal for the conversion, that is hexadecimal to binary number. binary number. Hexadecimal to binary number. So 166 can be converted very easily into a binary number. So take each digit, okay. So 1, hexadecimal 1. Now this should be converted into binary number. So the value 1 remains as the remainder of this process, because 1 is lesser than 2, 1 cannot be divided by 2. So 1 is the result of the hexadecimal 1, but remember we have to add 4 zeros towards the left side to make it as a group of 4 binary digits. The next number is 6. 2 3s are 6, remainder is 0. 2 1s are 2, remainder is 1. And 1 cannot be divided. It is better as it is. Okay. So the result of this is 110, 110. But we don't have the fourth bit. To make it the fourth bit, we can prefix 0. The another digit is also 6, we can rewrite as it is. So the final number is, we can eliminate at the end of writing this, okay, 1 0 1 1 0 0 1 1 0 is the binary equivalent of 166. That is matching with this, you can compare. This is how the binary to hexadecimal and this hexadecimal to binary conversion takes place. So, from this I am concluding today's session. We will continue in the next class. In the next slide you can see what are the working exercise you can do at home.